The previous design looked at implementing this equation using inverting op amps. We're also going to implement it, but we're going to try to minimize the number of components. One way of doing this and seeing this is looking at this equation and rewriting it as follows, where our second in design will involve VO is equal to -2 times -2.5 times V1 minus 2V2 times minus 2V3. In this design and example, it shows that we can use several ways to solve a given design problem. One way to evaluate the different designs is to use a minimum fewest components criteria, in which we can apply the smallest part count in this example. And that's what this design is going to do and show. In the previous design, it required 3 op amps. Here we're going to only use 2 op amps. Okay, so for this design, let's draw a block diagram. So here we have V1 multiplied by a -2.5. So here we have V1 multiplied by -2.5, and then we have V2 multiplied by, in this case, -2. We're gonna add these two outputs together. So the output of this guy is -2.5 times V1. The output of this amplifier of -2 would be -2V2. This is a summer, so the output of this summer is -2.5 V1 minus 2V2. Okay, and we're going to amplify this by -2 from the output shown in this relationship here. We're also going to invert V3 with a gain of -2, and that's our term right here. And then we're going to take these two outputs and then resulting in our output VO, which is basically -2 times -2.5 V1 minus 2V2, all that multiplied by -2 as shown here, and then we got a -2 times V3, so that's -2V3. Okay, we put a plus here and then a minus here to illustrate that. So here's our summer. Okay, so the output coming out of here is 2 times -2.5 V1 minus V2. Next, we'll show you the circuit realization using op amps to implement this block diagram. So here's our circuit realization using op amps. So here for the one in brackets, it's implemented in this dashed red line, in which we have a gain of -2.5 for V1 and a gain of -2 for V2. This can be shown here, which is configured as an inverting summer. 50 divided by 20 is a gain, since this is going to our inverting input of the op amp, this is a gain of -2.5. So -2.5 times V1 is shown here. So it's -2.5 times V1 and 25K and 50K. So 50K divided by 25K for V2 is a gain of -2 V2. So that implements this one in brackets. And then this has an overall gain of, we're going to take this overall output and multiply it by -2. And here again, drawn in green for this input to this summer again, the second summer, 50K divided by 25K is a gain of -2. So this is our implementation for the V1 and V2 inputs. Then finally for V3, we have a gain of -2, and that's 50K over 25K, that's -2. And notice we have a gain of -2 for this output of the first summer, and a gain of -2 for V3. So our output coming out of here, 2.5 V1 minus 2 V2 minus 2 V3 when you add these two inputs right here. So here we have the minus 2 V3 for this input leg, and then minus 2 times 2.5 V1 minus 2 V2 for this leg right here. And that concludes this design. Again, this one uses 2 op-amps to implement this circuit right here. And we wrote this circuit so we can, we wrote this input-output relationship in terms of this equation to see how this can be realized in terms of op-amps. So this uses 2 op-amps in this second design. The first design uses 3 op-amps. And that concludes this example.